In this lab, I was tasked with creating a computer model to simulate the motion of a star in orbit around a black hole of unknown mass, with the only force acting on the star being the effect of the black hole's gravity. Net force data generated by the computer model was then used to find the mass of the black hole. Ultimately, the mass of the black hole that I calculated varied according to the point in time of the experiment, but the average mass value over the course of the entire experiment that I found was 9.679 times 10 to the 34 kilograms. This lab was carried out to gain a better understanding of the nature of a single force, specifically gravitational force, the factors that affect its magnitude, and its effects on motion. As in our two previous labs, our fundamental principle used in this experiment was Newton's second law, the idea that total force is equal to mass times acceleration, or the rate of change of velocity. Velocities were found by finding changes in position over changes in time. When the star's mass is factored in as well, change in momentum over change in time is given. Newton's second law assures us that this value, dp dt, is equal to net force. Also necessary in this experiment's calculations is the equation for gravitational force. As you can see, the magnitude of gravitational force is a direct result of the masses of both objects in consideration and the distance between them, or r, as well as Newton's gravitational constant, which is equal to 6.7 times 10 to the negative 11. These physical principles will be necessary to create an accurate computer model. Here are the system's initial properties. The mass of the star is 2 times 10 to the 30th kilogram, and the time step is equal to 24 hours and seconds. After velocity is calculated at each point in time in the experiment, the code calculates change in velocity for each time step and then factors in the star's mass to establish changes in momentum. These changes in momentum over changes in time are equal to net force, according to Newton's second law. Parallel and perpendicular components of net force are also calculated. At each point in the experiment, net force calculated is used to find the mass of the black hole by solving the equation for the magnitude of gravitational force for the unknown mass of the black hole. Note that because the black hole is at the origin of my coordinate system, r is equal to the magnitude of the star's position vector. This process of finding black hole mass is carried out with this line of my code. Also, my code was set up to find mean mass value of each of the mass calculations made throughout the experiment, which is printed with this line at the end of the program. Here is my program when it is run. The yellow arrow represents net force. It always points to the source of the gravitational force, the black hole. The red arrow represents the perpendicular component of net force, which is the force that changes the star's direction of motion. This arrow always points to the center of the kissing circle. The black arrow represents the parallel component of net force, which affects the speed of the star's motion. As the object speeds up because of the strengthening gravitational pull of the black hole, the arrow points in the direction of motion. As the star moves away from the hole and slows down, the arrow points in the direction opposite to motion, and at one point the arrow disappears, which means that the star is at constant speed, and the only force acting on it is perpendicular force. How are these perpendicular and parallel components of net force different from the perpendicular and parallel components of change of momentum? This is an example of a cause and effect relationship. For example, the perpendicular component of net force is what causes the star to change direction. The perpendicular component of the rate of change of momentum is the rate at which the star's path changes, or its path's curviness. It is strongest at the ends of the star's ellipse of orbit, where the star's path changes direction. Similarly, the parallel component of net force causes the speed of the star to change. The parallel component of the rate of change of momentum is the rate at which the star's speed changes, or its acceleration. It is strongest in the flat parts of the ellipse of the orbit, as the star moves toward the black hole or away from it. The factors that affect the magnitude of gravitational force are Newton's gravitational constant g, the masses of the two objects in question, and the distance between these two objects. G is universally constant, so if the black hole in this experiment were replaced with another black hole, and the star moved in the same exact orbit around it as it did in this experiment, the distance between the star and the black hole would be the same at every point in this new experiment as it was in the first. Thus, it would be impossible for the motion of the star to remain unchanged if the new black hole had a different mass than the first one did. This new black hole must have the same mass that the first one did.